Hi, welcome to this introductory video on trigonometry. I'm going to try and talk you through some basic concepts of trigonometry and then introduce the idea of how these are used in engineering to calculate things like forces, measurements and dimensions. One of the first things I wanted to do was just look at the relationship between trigonometry and triangles and circles. So we're going to need to get your equipment and maybe work along with me. So you're going to need to get yourself a pen or a pencil. You will need a pair of compasses. A short ruler will be fine, and you will need to have a protractor handy. Okay, if you've got all those pieces of equipment, now what I want you to do is I want you to draw a quarter of a circle. So we're just going to use the top right hand corner of the circle. So I'm going to set myself a line on my page, and I'm going to enlarge this slightly. So I'm going to use 10 centimeters, and we're going to see the relationship of the length of the lines as we look at the different angles that we get in trigonometry, and hopefully you're going to sort of see how trigonometry works. And I often find it's really useful when trying to understand a new engineering concept to draw it out, to sort of visualize it and see it as I'm working it through. I think it helps construct an understanding in your mind. So I'm going to mark this off for convenience sake. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's the radius of our quarter circle. I'll just number these off for ease. And 10. I'm going to do the same at the side here. And so you can watch this video and then you can do this activity yourself. Hopefully you'll start to build that visualization in your mind and understand the concepts that we've been talking about. So there is a relationship in a right angled triangle. There's a relationship between the angle and the length of the sides, and we've used this, you might have used this in school, but I've used this exercise as a way of sort of visualizing how that ratio, the change in length, works as we go through the different angles. So I'm going to start off with a 30-degree angle here. So I'm going to use my protractor, I'm going to mark off 30 degrees, and then I'm going to mark through that line out to the edge of my quarter circle. And this is the radius, and it doesn't change. The radius is always going to remain the same. But it's also going to act as my hypotenuse. So the radius is also going to be the hypotenuse. I'm going to make that a little bit darker so it stands out. And you can see that that's 10 centimeters long. So in the real world, that could actually represent something that's 10 centimeters long, or it could represent something else. For example, it could represent a force of, say, for example, 10 newtons. And that could be 10 newtons acting in this direction. And there's a ratio then here, the length of the line of the two of the sides of our triangle. I'm going to draw those in. So we have our angle here, which is 30 degrees. And we have here our opposite line. Just label that as opposite. Like so. And I wanted to look at the relationship of the length of the opposite line in relation to the hypotenuse. And if we're looking at this, you can see that the length of that line on our little graph is, I'll just do a little dotted line, 5 centimeters. And that's interesting because that's half the length of the hypotenuse. And if I borrow a calculator here, I'll put that in. If I look at, now you might be familiar with, but I'll just put them up here anyway. I use this, it's SOH, CAH, TOA. You might have learned this in school. So it's the sine is the opposite divided by the hypotenuse. Well, I've got the opposite here is 5, divided by 10 would be a half. And actually, if we try that in a calculator, switch mine on, and I put sine of 30 degrees is equal to, it's equal to a half. What that basically means is if I've got a distance or a measurement here of some description, and it's acting at an angle of 30 degrees, then the vertical component, this component here, the amount of force, so 10 newtons acting in that direction, I would have half the force acting in that direction. So this would be a force of 5 newtons, or a distance of 5 centimetres, or kilometres, or whatever unit that you're measuring in. You will actually also see this in electrical electronic engineering. So the application of trigonometry is vast. It's in all aspects of engineering in all different areas: dynamic, static, electrical, electronic. It can be quite varied, and so it's an important skill to learn and understand. If we just complete our triangle, we can see that the adjacent length, we'll colour that one in green, so do that like so. So this is the adjacent, and you can see here that it's about 8.5. In fact, if we use our calculator, so now we've got the adjacent and the hypotenuse, and the adjacent and the hypotenuse would give us the cosine. So the cosine of 30 degrees multiplied by the length of 10 newtons will tell us what the length of the adjacent is. Well, if we look at this, we can see that cosine of 30 is, now you'll notice these a little bit later on, these are called trigonomic identities. So we had the trigonomic identity of a half, and now we've got, so that was for sine of 30, and now we've got cosine of 30, and we've got root 3 over 2. Don't worry about that at this time. We can just look at that as a decimal, and as a decimal it's 0.866. So this was half, or 0.5. I sometimes like to think of it as 50%. It's 50% of the force, or it's half the force, and here it's about 86.6%, or 0.866. Put that in there, 86.6%. So actually, if we look now at our graph, you can see that that probably is at about 8.6 centimetres. So any given length in your triangle, the hypotenuse, so if this was 20 centimetres, 20 newtons, then this would be 10, this would be half of that, and this would be multiplied by 0.86, so it would be 17.2. Well, let's lose our calculator and just double check it. So if we've got a length of 20 metres, and we multiplied it by the, using cosine because it's adjacent, cosine of 30 degrees, like so, it would give us 17.32 metres. So that is that relationship, and that's given us these two common trigonomic identities, two things that we would regularly recognise and see in engineering. Right, now we're going to just look at how, if I move this, if I increase this angle, I'm going to keep this same distance, but I'm just going to move round. You'll see that this relationship will change, but some aspects of it will remain the same. So I'm going to look at 60 degrees and draw a line through there. Now to retain this length at 60 degrees, you'll notice that the opposite line has actually increased in length. It's had to increase in length. This length has remained the same, but the opposite has had to increase in length. But while that is happening, the adjacent angle has decreased in length. And what we're actually going to see is another part of the trigonomic identities, because you can quite clearly see here that my drawing's a little bit rough, but you can quite clearly see that that's going to be around, or it is, 5 centimetres. We know that this was 10 centimetres in our drawing, or it's going to be representative of 10 newtons. We're looking at the adjacent angle, so we had our 10 centimetres, and the cosine of, and we're now working at 60 degrees, and it gives us 5, because cosine of 60 is equal to a half. So the sine of 30 is a half, it's 0.5 or 50%, and that is also equal to the cosine of 60 degrees. And I think you may be seeing now the relationship of this line here. If this is 5 centimetres, you can see that this is increasing length. And if we go across on our graph, just to help us out, I think you know what's going to happen here. It's approximately 8.6 here. And again, we can confirm this. So now we're looking at the opposite. So opposite is the sine. So our distance, or our value, 10 newtons, 10 centimetres, multiplied by the sine of our angle, 60 degrees, is equal to 8.66. Just move that slightly so it's not like, there you go, 8.66. So you see the relationship is maintained even though the triangles look different. We will look at a third one, just to sort of illustrate a point. And another common trigonometric identity. If I go at 45 degrees, just here, and I'll do that in a different colour, so it stands out more. So we're going to go for nice light blue. And I've got my 10 centimetres. Now it won't surprise you to realise that this is actually very similar to a square. Basically, if you drew a square and you had 90 degrees in the corner and you went halfway through, you would get 45. But if I was doing this as a right angled triangle, and this was maintaining that 10 centimetres, then you can see that these lengths are roughly 7 centimetres, and of course they would have to be equal if they were forming a square, and the angle is 45 degrees. And we can check this. If we look at the sine of 45, we get root 2 over 2, or 0.7, let me slide this way so you can see it, 0.707. Great, so let's do the cosine of 45 degrees, and let's just confirm that for ourselves so we know that we've seen it and we can believe it. And again, root 2 over 2, it's 0.707. So if this was a force acting in this direction, then this would be about 70%, or 0.707, depending on how you wanted to, how accurate you wanted to work. So we can see that the sine, the cosine, as the angle changes, the ratio of the lengths change, but they maintain this length of the radius of our circle. You can try this, and I would very much encourage you, after you've seen this video, to spend a couple of minutes just exploring a few others, just to sort of check, you know, prove it to yourself almost. So if I looked at something that's 15 degrees there, so that would be not quite 90, I'm going to 75 there, 75 degrees, 75 degrees. And if I check on a calculator, my 10 newtons of force acting at, let's look at the opposite angle. So I'm going to go with sine of 75 degrees. Now it should be, as we look across on our graph, it should be sort of about here somewhere, so it should be 95, 96, somewhere in that region. So let's try that. And it is actually 96, or it would be 9.6, so there's 9, yeah, 9.5, 9.6, about 96% of the overall length. And the force would be acting in that direction. And of course the cosine, you'd be able to look at that and go, well, it will be about 2.5. Let's just double check it. There's my 10 times the cosine this time of 75 degrees. And that's giving me 2.58, 2.6. I hope that's been useful. I hope that sort of helps you see how the relationship between the sine and the cosine, the opposite and the adjacent, maintain this relationship within the circle, so that the right angle triangle always maintains the same length, the hypotenuse. And hopefully later on we'll explain to you how these can be thought of, rather than just thinking them as measurements, actually thinking them as a scale model for forces such as Newton's acting in a system. Have a go, have a little practice, try a few different triangles, use your calculator to check how it matches your graph. And the hope is that the visualization of the trigonometry happening will help that build a model of trigonometry inside your head as a learning activity. And when you see these questions and problems, you will sort of, yes, when a force is acting at an angle, I can actually separate it into its opposite and its adjacent. And we'll be looking at that in the next video. Thank you very much.